So let's finish up the conversation this week by talking about free energy. Gibbs free energy is the energy available in a process after taking into account the energy lost by entropy. So free energy is equal to the total enthalpy of reaction, we talked about this several months ago, minus the temperature times the entropy. So if you take the total energy in a process and subtract that part of the process that is consumed with the change or the randomness of the system, then what is left is the free energy. And so the change in free energy when a reaction occurs is equal to the change in enthalpy minus the temperature in Kelvin times the change in entropy. And of course, if we use standard calculations, then the standard free energy is equal to the standard enthalpy minus the temperature times the standard entropy that we just calculated in the last problem. And the sign of the free energy will tell you whether or not a reaction is spontaneous or not. And what you can see is that if the free energy is zero, then the reaction is in its current state is at equilibrium and will not change. If, on the other hand, the free energy is negative, then the reaction will proceed spontaneously to the right, forming more products. And if it's positive, it will not proceed. So, for example, you have a way of calculating the total entropy times the temperature. The enthalpy represents the entropy of the surroundings times the temperature, and the T delta S is the entropy of the system. And so let's take these couple of these equations here and look at whether or not this reaction that I've shown here will proceed spontaneously. Or let's first calculate the free energy change at 25 degrees centigrade. So how would we do that? So let's look at how we would do that. First of all, we have to write down the equation we have here, and we've got hydrogen gas plus methane. So this is the same reaction we calculated before, so that'll save us a little time. And that goes to form methane gas. And what I've shown you here is the standard enthalpy for each of these, and then the standard entropy. So the enthalpy, H0, the calculation is the same, and for a element, enthalpy is always 0. For ethene here, it's 52.4, and for ethane, it's minus 84.0. And so the calculation of delta H here is exactly the same as what we just did with delta S. So delta H is going to equal the sum of the products, which in this case is going to be minus 84.0. That's the sum of the products, minus the sum of the reactants, which is 52 plus 0. 52.4 plus 0. So delta H0 is going to equal, adding these two numbers up, it's going to be 136.4, and that's going to be negative. And these, notice it's kilojoules per mole. So that's the answer there. Now in the previous, we already calculated delta S0. So let's take a look back at what that number was. It's right here. You see, this is the same reaction. So this minus 121.57, minus 121.57. Now watch the units here. This is going to be joules per mole degree Kelvin. Okay, so it's joules instead of kilojoules. So when we do this calculation here, we're going to have to take that into account. Okay, and so the temperature here is 25 degrees, so T is going to be 298.15. So delta G is going to equal delta H minus T delta S. So that's going to, delta G is going to equal minus 136.4 kilojoules minus 298.15 times, and we can move this over 3 spaces to make it kilojoules, a minus 0.12157 kilojoules per mole degree Kelvin. And so we had to move that over in order to make them both be kilojoules. So let's take a look at this calculation. It's 0.12157 times 298.15. So that's going to equal a minus. So it's going to end up being minus a minus or plus 36.25 kilojoules per mole, because we took into account the temperature. And then this is going to be 136.4. So delta G is going to equal this added together. And if we subtract 136.4, we get 100, a minus 100.2 kilojoules per mole. So per mole of this or per mole of this, the free energy is going to be a minus 100.2 kilojoules. So this, based on this previous statement here, if it's negative, it proceeds spontaneously. So negative here tells us that this reaction is going to proceed spontaneously with any outside influence. Now, as it turns out, if you take all the possible scenarios for enthalpy and entropy, you can get one of 4. You can put those in a 2x2 box. The enthalpy can be positive, that is endothermic reaction. The enthalpy can be negative, an exothermic reaction. The entropy can be greater than 0, so it's an increase in entropy, or less than 0, that's a decrease in entropy. If the entropy is increasing in an endothermic state, then delta G is negative at high temperatures and proceeds spontaneously. It's positive at low temperatures and does not proceed. So it is a process that is spontaneous at high temperatures. If there's an increase in entropy in an exothermic reaction, then it's negative at it's less than 0 at any temperature, so it proceeds spontaneously. If, on the other hand, there's a decrease in entropy and an endothermic reaction, then it's positive at any temperature and it will not proceed at any temperature. And then, conversely, if it's a decrease but exothermic, then it's positive, or it's negative at low temperatures and positive at high temperatures, so it only proceeds spontaneously at high temperature. Now these plots show that how the delta G varies with temperature, and that, again, with the 4 combinations we just spoke about. So here's the free energy on this side and the increasing temperature here. And this is this first line represents an endothermic reaction with a decrease in entropy. So no matter what the temperature is, this will not proceed. This is an endothermic reaction with an increasing entropy. So at low temperatures it does not proceed, but at high temperatures it does. This is an exothermic reaction, but a decrease in entropy, so it proceeds at low temperatures but not at high temperatures. This is exothermic and an increase in entropy, so it is spontaneous at all temperatures. And this shows you the same idea. We've substituted. So let's take a look at this. You have, again, endothermic with an increase in entropy. It proceeds at high temperatures but does not at low temperatures. And the 4 values, just like we went through the last time. The incomplete combustion of carbon is described by the following reaction. Predict how the spontaneity of this process depends on temperature. And here's another one. The popular chemical hand warmers heat by air oxidation of iron, shown here. Predict how the spontaneity of this process depends on temperature. So what you need, if you look at this, this is going to be, you have a solid plus a gas goes to form a gas. So there's going to be a increase in entropy. So you're going to be in this situation. So if this process is exothermic, then it is not dependent on temperature. If this process is endothermic, then it proceeds at high temperatures but does not proceed at low temperatures. So that's what this shows you. This is the opposite. This shows a increase or a decrease in entropy. So you're in the bottom row here. A decrease in entropy is the bottom row. The bottom row is if this is an endothermic reaction, then it would be not spontaneous no matter what the temperature is. If it's a exothermic reaction, it's spontaneous at low temperatures but not spontaneous at high temperatures. Now you just have to do several of these, look at several of these to get used to how to work that out.